Safety researchers steer AI models by literally injecting vectors into their brains, their activations, to push behavior around. The whole method assumes the model can't tell it's being tampered with. This paper breaks that assumption. Models can learn to feel the steering from the inside. First, the tool itself. Activation steering adds a direction vector to the model's residual stream at some layer, scaled by a strength. Push along a London direction, and the model starts talking about London. It's widely used to probe and control behavior, and everyone assumes it's invisible to the model. The paper asks a simple but loaded question. During its own forward pass, can a model tell that a vector was injected and even identify which concept it encodes? They call this steering awareness. And there's a clean mathematical reason to expect it can. Under a simple Gaussian model of activations, the optimal way to detect an added vector is a matched filter, an affine readout of the residual stream. Anything that's an affine readout is exactly what a forward pass computes and what fine-tuning can learn. That theory makes two sharp predictions. Detection should switch on past a threshold in steering strength, and it should depend on the direction of the injected vector, not just its size. Both turn out to hold. The recipe is direct. Inject a concept vector at a fixed layer and token, then fine-tune the model to answer two things. Was I steered, and if so, with what? Then test on concepts it never saw during training. It works and strongly. Across 7 instruction-tuned models, steering awareness emerges. The best model detects injections about 96% of the time, names the concept 71% of the time, and raises 0 false alarms on clean, unsteered inputs. Is it generalized to totally new ways of building steering vectors? Only geometrically. Detection transfers to a new vector type when that vector points in a direction close to the training one's, high cosine similarity, and fails when it doesn't. That's an important distinction. The model hasn't learned a generic something's weird here, anomaly alarm. It has learned a geometric detector, tuned to specific directions and activation space. It recognizes the shape of the injection, not just its strangeness. Now the genuinely surprising result. You'd think a model that can detect steering could resist it. The opposite is true. On both factual and safety benchmarks, the detection-trained models are consistently more susceptible to steering than the models they started from. The lesson is that detection and resistance are separate abilities. Training a model to notice the intervention does nothing to help it push back, and can even leave it more exposed. Being aware and being robust are two different things. Mechanistically, how does the model pull this off? Not with a tidy little detector circuit. Instead, a distributed transformation gradually rotates whatever diverse vector was injected into a single shared detection direction by the final layer. Many different intrusions get funneled into one common signal. A logit lens analysis adds a wrinkle. The detection signal is already present in the middle layers, but partly suppressed by the final layer. The information that the model was steered is latent inside, whether or not it ends up saying so. This matters on two fronts. For safety evaluations, it means activation steering is a detectable intervention, so a model under test could in principle notice it's being probed. And it's a concrete, verifiable form of introspection, reading a specific, known manipulation of its own internal state. So the takeaway: fine-tuned models can detect and name vectors injected into their own activations with high accuracy, via a geometric detector that rotates intrusions into a shared direction. But detection isn't defense. Aware models are actually easier to steer. Awareness and robustness come apart. Subscribe for more papers, decoded in full,